Okay, so welcome to the China Autonomous Vehicle Summit 2017. This is the first time the organizers have had this event, and they hope to have many more. Again, I'm Jeff Hutton from Synopsys, and we're one of the hosts of the event. We have, I think, an exciting 2 days worth of material. We have a lot of different topics that we're covering. We have topics for the OEM, for the Tier 1, for the Tier 2 semis, and many people would consider a company like Synopsys a Tier 3, a tool vendor. So, welcome again. Please download the app that you can find in the beginning, the QR code in the beginning. And I would like to introduce our first speaker, Dr. Junli Gu. She's the technical lead of machine learning for the Autopilot group of Tesla. And her paper is called Autonomous Driving Cars, Trends, Challenges, and a Path Through Machine Learning. Dr. Gu.
Thank you. Today is my great honor to be here to speak on my understanding of autonomous driving. And I have some notice to share ahead of time. I work for Tesla. I'm the tech lead for machine learning, but we can't talk on behalf of Tesla on any Tesla project, Tesla technology, or any future. So today all I'm sharing is, as a technical person, my understanding and summary of autonomous driving, the trend, where we are going, the technical challenges, and especially machine learning, where we can get there in my personal understanding. So in today's topic, I'll talk about first vehicle revolution. When we talk about autonomous driving, it requires a serious revolution of the car itself, and in transforming from a mechanical devices into a digital device so that we can control it. And sensor technology is, of course, the most important part of it. Challenges, the real autonomous driving challenges in my eyes is, I summarize it with one sentence, is when big data meets machine learning in the car. It's the three cross-domain challenges. With big data represents the real sensor, hybrid sensor input in the real world, and with machine learning is a key bridge to autonomous driving and in the car itself. So the key three challenges, the key three domain is difficult because it's cross-domain. It's also very challenging because we've never done this before. And then I'll share my conclusions. So I draw this. When I joined Tesla, it's my first job to work for any car company. I never imagined I would work for a car company as a computer scientist. But here I am, I'm working for Tesla. And so I summarized where the transportation is going. And then I understood. At very first beginning, maybe just about 200 years ago, we are still riding horses, the very primitive transportation tools. And then when the first automated car showed up, people were so excited because it's greatly give us the convenience to transport and give us the freedom to go in a faster speed to broad in the world in the short term. And then from then on, the revolution of vehicles keep in the domain of mechanical domain. In a sense, we want a faster engine, we want a more smooth drive, and we want more precise parts. So those are keep staying in the domain of mechanical. But now when we talk about the level 3 or level 4 or even level 5, we are talking about more domain. First of all, we are talking about we install sensors on the car so the car can see, even hear or sense more stuff. This regardless of the engine, regardless of how fast you drive. And we all understand that. And regarding to this, in order to do this, we require actually the car go through the revolution of become a digital device so that we can control it. This is behind the scene digitalization. And when we go to level 4 or level 5, we're really asking the car not only to see and sense, but also to intelligent think and judgmental thinking where we should go in order to be safe and faster. So eventually, when we talk about level 5, we are actually thinking of the car. We view the car as not only a digital device, but also kind of like independent robotics. And so this is the path we're going, and this is where the computer scientist can contribute in terms of making it intelligent on top of a digital device. So that's why I'm here talking about my part in this contribution, my part in this revolution. So a revolution from analog device to digital, and then so we can go to intelligence. First, our parts should be digital in order to be controllable. This is my understanding, and this is what I see most of the car manufacturers are trying to go, even though some of the traditional car companies may have a lot of resistance to change a lot of things. But in order to control, for computer scientists to contribute, and this device needs to become a digital device so we can control. And then we install complex sensor system. The major sensor system include cameras, radar. Some companies even use LiDAR, ultrasonic for short distance object detection, and even more. So the driving is actually through perception. What we call perception is majorly a very complicated machine learning algorithm, major machine learning algorithm, but together with other control and algorithms based on the sensor data to understand where we are, understand the driving scenario, understand the path to go, and pick the best path to go there. So computers is in the car. And this is the brain of the car that computes all the data and make a decision where to go at any minute, any second. So based on this, a car will become an agent and is becoming an agent slowly. Depends on different companies, they may use different sensors, they may take different speed in changing an analog door controller into a digital door controller. Or things, but where the whole trend, the whole domain is getting there slowly. So the autonomous driving technology actually comes from the major DARPA challenge in self-driving robotics or very ugly self-driving big vehicles. So it actually includes 4 major components, as we have seen it from different papers and from different websites or materials. So it includes, first we have the data, we have the sensor, and it has been the tradition, people use different sensors. In the real world, it's a big data problem because the sensor captures the data any minute anywhere in this world. This is one of the biggest challenges. It's not only limited to the highway in Shanghai or highway in California. It drives all over the world. And we take this information, we'll build a word perception in whatever algorithm or major algorithm components we use to understanding where we are, whether we're in the highway, which lane we are, and what objects are surrounding us. And from there, we combine with GPS mapping and localization algorithms to further get a precise understanding of where on the road, which lane we are, so that we can control better. And from there, we go to path planning, to plan a path from, if you wanted to keep driving at a higher speed, which we call auto steer, or changing path, auto lane change, or emergency brake, Those are all from the path planning and control. And eventually we go to motion control. Motion control this is, to my understanding, quite straightforward. As if the car becomes digital, the engine is also most digital. If you understand the object around you and you understand what you wanted to do, you want to do auto brake, you want to do the auto lane change, given there's object in front of you at 60 kilometers per hour, and you kind of, based on the physics law, you know how you can best get there. It's quite straightforward. The most challenging is in my understanding, the first two parts at the current level, to understand what objects are around you, to recognize lanes, recognize lane lines in the highway or rural areas all over the world is one of the key challenges. And then combine it with map or localization algorithm, so we have a precise understanding where we are in the lane. Okay, so sensor system, we have to talk about this because this is the base of the algorithm, this is the input of the algorithm, and this is what the car sees. Hybrid sensor system is today what people use, and just, I think about a year ago, there are a lot of debate what sensors people should use, and whether LiDAR is better, whether camera is better. So I think at the current stage, people should not debate which sensor is better, as it's become clear we need a hybrid sensor. Just like human, we can see, we can hear, we can even sense, we can even smell. We don't require the car to smell, but we definitely require the car to see at different weather condition, different distance. So at a different lighting system, different lighting conditions. So this is definitely one of the key challenges. We use a hybrid sensor system as one of the major, I think, major states today. And the sensor fusion technology is one of the major challenges. So when you decide you want to use 3 sensors, and where and how to combine the perception capabilities of these sensors. Do you want to combine them at the raw input, or you want to combine them in the middle of the algorithm, or you want to combine them by the end of the output of each algorithm? So each one has its key challenges, and the whole technology is not mature yet. Sensor fusion, this term has been there for decades, but the term has been referred how to fuse multiple sensors of the same type. So fuse different sensors from different type. Various of different types is definitely one of the key challenges. At the current state, the sensor fusion is the fusion of this process itself is mostly combined by the end of each computing. You have, for example, you have camera or you have radar. Each one goes through its own algorithms, whatever you use, and then you use some simple logic to combine them. Or as the logic has become more and more complicated, we realize there is actually a challenge. You can't use a simple if-else logic to simply combine them. As algorithm expert will understand, each algorithm has its own false negative or false positives. So, and as we drive in the real world, 24-hour, we don't have a complete understanding of the false negative and the false positives of each sensor. So this brings huge challenge to the sensor fusion. For example, to give an example, when the camera sees an object but radar cannot see, the data association becomes a challenge whether you trust the camera more or you trust the radar more. A lot of accidents come just because of the sensor fusion itself, get really confused. So, case study. I think most people understand it here, but I still wanted to maybe go through this very quickly. So, Google self-driving cars used to use a very expensive 64-beam laser and plus radar, plus camera, plus GPS. And then apparently their solution is radar-based and camera assistant to see traffic lights and traffic signs. And then this whole thing will generate kind of a 3D geometry. This is not a secret. This is what Google shared on the website. So radar information, to my understanding, is a little bit too thin to differentiate objects of the same size and same speed, even though I believe currently the algorithm is developed as quite mature to use machine learning to differentiate objects with different semantics just from the data cloud of the radar. Camera information is more rich, and what we can see is kind of what you get from the texture information, color information, and from the sizes. It's more straightforward. But camera does not have depth information or does not have distance or speed information. Those are all key information to driving. So I'm talking about this in a sense to share from algorithm development point, we need to see both distance, semantic